Welcome to Central High School's IB Physics Unit 3. I'm Mr. Tompkins, and we are going to discuss how objects behave when their temperatures change. Previously on thermal physics, we learned that elements are the building blocks for all matter in the universe. Molecules are made up of more than one atom, and the mole is used to convert from atomic mass into grams. 1 mole equals 6.022 times 10 to the 23 atoms. And 1 mole of an element equals the atomic mass of that element in grams. The energy lost due to friction is converted into thermal energy, or heat, which is given by the variable capital Q. And temperature is measured by a thermometer and is in degrees Celsius, or Kelvin. There are 3 phases of matter: solids, which have a finite shape and volume; liquid, which has a changing shape but a fixed volume; and gas, that has no fixed shape or volume. Heat is transferred through a process called conduction, where atoms of 2 objects bounce directly off of each other. Heat always transfers from objects with higher temperature to objects of lower temperature until they reach the same temperature. This point is called thermal equilibrium. Thermal properties is the second lesson in thermal physics. In this lesson, we will determine formulas to predict temperature and phase changes in a substance. Here are the objectives that we will cover in this lesson. You will receive a copy of these on your checklist. When we add heat to an object, the object's temperature will increase, but how much it increases depends on certain properties of that object. What are some things that can affect the temperature change of an object? Let's do a quick thought experiment that we see in our everyday lives. I place 2 identical pots on my stove, one that contains 1 kilogram of water and another that contains 1 kilogram of vegetable oil. They're both at room temperature. After 2 minutes, I test the temperature of the water and the oil. Which substance do you think saw a greater increase in temperature, the oil or the water? Well, it's the oil. Why do you think their temperature changes so differently? Well, it's because they're made out of different materials. Now I place 2 identical pots on the stove. This time they are filled with 2 kilograms of water and a half a kilogram of water. They're both at room temperature. Once again, after 2 minutes, I test the temperature. Which pot do you think has the higher temperature? Which pot will take less time to boil? Well, it's the half a kilogram of water. Why? Well, it has less mass or less water in it for it to heat. So there are 2 things that affect an object's increase in temperature, and that is the material the object is made out of and its mass. The thermal capacity. The amount of heat energy required to raise the temperature of an object 1 degree Celsius. It is given by the variable capital C. It has the units of joules per degree Celsius. We use this when we do not know the mass of the object or if the object is made up of different materials. It is specific only to that object. So what the thermal capacity of one object is not necessarily the thermal capacity of another. And it's found using C, capital C equals Q divided by delta T, where C is the thermal capacity, Q is the amount of heat energy added, and delta T is the change in the object's temperature. Now we're talking about the specific heat capacity. It's the amount of heat energy required to raise 1 kilogram of a substance 1 degree Celsius. It's useful when we know the material and how much of it we have. It is only material specific. It does not require the mass. So the specific heat capacity for 1 kilogram of copper is the same as the specific heat capacity for 10 kilograms of copper. It has the units of joules per kilogram degree Celsius and is given by the equation the specific heat capacity equals the amount of heat energy added divided by the mass divided by the change in temperature. How do we find a substance's specific heat capacity? Well, the answer is we measure it. Usually we'll place a substance with a known mass and temperature into water with a known mass and temperature. Using the specific heat capacity of water and the temperature that they reach at thermal equilibrium, we can determine the specific heat capacity for that substance. Here's an example. I take 1 kilogram of water at 0 degrees Celsius and a half a kilogram of copper at 100 degrees Celsius. I know the specific heat capacity for water is 4,200 joules per kilogram degrees Celsius. I then place the copper rod into the water and measure the temperature change for both the water and the copper. The temperature change for the water is positive 4.3 degrees Celsius. The temperature change for the copper is a negative 95.7 degrees Celsius. Heat has traveled from the copper to the water. We take the equation for the specific heat capacity and rearrange it to solve for the energy. We must assume that all the energy gained by the water came from the loss of the energy from the copper. This isn't true if some of the energy is gained by the water is from the environment. In order to counteract this heat transfer, we'll need to use some kind of insulated container. Substituting the energy equation above, we get this new equation. Using algebra, we rearrange to solve for the specific heat capacity of the copper. And plugging in the numbers and solving, we get the specific heat capacity of copper to be 380 joules per kilogram degrees Celsius. Well, if we use water to find the specific heat of other materials, how do we know what the specific heat of water is, or the specific heat capacity of water is? Well, I will give a 10% bonus on your lesson quiz if you can answer this question when it shows up on that quiz. Google it, find it out. It's a good, easy bonus points. Just to review, there are 3 phases or states of matter: solid, liquid, and gas. The more heat energy a substance has, the less constricted the molecules, and the further to the right it moves, from solid to liquids and then to gases. Each phase of matter can turn into the other phases of matter directly. From a liquid, we can turn into a gas, and it's called evaporation. A liquid into a solid is called freezing. A gas into a liquid is called condensation. A gas into a solid is called deposition. From a solid into a liquid, it's called melting, and a solid into a gas is called sublimation. Write this diagram down in your notes so that you know what these terms mean. A phase diagram shows how a substance will appear for a given temperature and pressure. There are some important parts to a phase diagram. We have what's called the triple point. Every substance has a temperature and a pressure where they can exist in all 3 states, solid, liquid, and gases, at the same time. For water, it is 0.01 degrees Celsius at a pressure of 0.006 atmosphere. Just so you know what an atmosphere is, the pressure inside the room that you're feeling right now is 1 atmosphere. We will talk more about this pressure in the next lesson. Then we have the critical point. The critical point is the temperature and pressure combination where liquids and gases are no longer distinguishable. So no matter how much pressure you apply to a gas at a temperature above the critical temperature, it will never turn into a liquid. It could possibly turn straight into a solid, though. Weird, I know. Boiling and evaporation. These are both methods of getting a liquid into a gas. Boiling happens at a specific temperature and only at that temperature. And it happens throughout the entire volume of a substance. Evaporation, on the other hand, happens at all temperatures. And it only happens at the surface of the liquid, not in the entire volume. So if you look in the pictures, I have a pot of boiling water. The water is turning into gas at all points in the water, all over the water. Whereas in the evaporation picture, I have a lake. And in the morning you get up and there's some lake fog out there. And it is just the surface of the lake is evaporating off due to the molecules escaping. How to increase evaporation? Well, we can increase the surface area by spreading the liquid out. You are allowing more molecules to become closer to the surface and escape. We can increase the temperature. This increases the kinetic energy of the molecules. The greater the kinetic energy means the molecules are moving faster, and this extra speed makes it easier for the few that are at the surface to bounce off and leave. We can stir the liquids. Stirring removes the slower molecules from the surface and allows faster moving molecules in the middle of the liquid to reach the surface and then escape. Or we can blow on the liquid. This removes a thin layer of water vapor trapped at the surface of the liquid and allows the liquid molecules to bounce through them and escape. Energy during phase changes. When we conduct an experiment, we notice something odd about an object's temperature versus energy graph. There are periods of linear growth where the object is gaining temperature at a rate depending on its heat capacity. But there are also periods where the temperature stays constant, even though we are putting a lot of energy into the substance. Why does the temperature stay constant? Well, if I look here at these places, it is only happening during the times when the substance is changing its phase. Notice how the energy required to make a total phase change is different for both the melting transition and the evaporating transition. In real-world measurements, temperature is lost to the environment. The graph will actually be somewhat curved based on the amount of energy being lost. The specific latent heat. It's the amount of heat required to change the state of 1 kilogram of a substance or material without changing the material's temperature. Latent means hidden. Because the temperature does not increase when the substance changes states, then that energy seems to be going in and hiding somewhere. It is a different quantity depending on the transition. For the freezing and melting transition, it is called the latent heat of fusion. And for evaporation and condensation transition, it is called the latent heat of vaporization. It has the units of joules per kilogram and is given by the equation the latent heat equals the heat energy into a material divided by its mass. So here's an example question. I have a 4 kilogram block of ice that I place on a 1200 watt hot plate. How long does it take the ice to melt completely if it has an initial temperature of negative 15 degrees Celsius? A 1200 watt hot plate provides 1200 joules of heat every second. Using the power equation, we get that the heat energy equals the power times the time. Remember this, we're going to substitute it in the next 2 slides to solve some of these problems. This is a 2-step problem. We must first figure out how long it takes to raise the block of ice's temperature to 0 degrees Celsius, and then at that point is whenever it can undergo the transition into melting, and then we'll figure out how long it takes it to actually melt. So to figure out how long it takes to raise the block of ice's temperature to 0 degrees Celsius, we're going to use the specific heat capacity equation, and we're going to solve and set it equal to the heat energy. And before, in the last slide, we said the heat energy was also equal to the power times the time period. Using algebra and rearranging, we find that the mass times the specific heat capacity of water times the change in temperature divided by the power of the heat of the hot plate is going to equal our time period. Substituting my numbers in and solving for the time period, I get that the time it takes to raise the temperature, that 15 degrees from negative 15 degrees Celsius to 0, is 210 seconds, or 3.5 minutes. We then figure out how long it takes to melt the block of ice. We're going to use the latent heat equation and solving for the energy, which once again is also equal to the power times the time. Using algebra and rearranging, solving for the time period, substituting our numbers in, and then solving, we get the time that it takes for the entire 4 kilograms of ice to melt is 7,600 seconds, or 126 minutes. So the total time to melt a block of ice is given by the time it takes to raise the temperature plus the time it takes to melt it. So it's 210 seconds plus 7,600 seconds. And the total time is calculated to be 7,810 seconds, which equals 130 minutes or 2.17 hours. Okay, just to recap what we learned in this lesson, there are 2 things that affect how a substance will gain temperature: its mass and the material that it's made out of. The thermal capacity, which is used for when we don't know how much of an object or how much mass of an object has or what substances are in it, is given by the equation the thermal capacity equals the heat divided by the change in temperature. Remember, this is object specific. The specific heat capacity, this is only material specific. It has nothing to do with the mass of the object. If we know the specific heat capacity, we can apply that to any amount of a substance. And it's given by the amount of heat energy added to the object divided by the mass and divided by the change in temperature. Phase changes. Any state of a matter can transform into any other state of matter. So a liquid to a gas is called evaporation. A liquid to a solid is called freezing. Gas to a liquid is called condensation. Gas to a solid is deposition. Solid to a liquid is melting. And solid to a gas is sublimation. Pressure temperature graphs. The two main points on the graph are the triple point, where you can have all three phases of matter at the same time, and the critical point where liquid and gases are indistinguishable. Boiling versus evaporation. Know these two things. If you have to, go back and look. Boiling happens at a specific temperature. Evaporation happens at all temperatures. Boiling happens throughout the entire substance, whereas evaporation happens only at the surface. Energy during phase changes. This type of energy is called latent heat because it's hidden. We put energy in, and it is hidden in the fact that the temperature doesn't increase. We call the latent heat during the transition of melting and freezing to be the latent heat of fusion. During evaporation and condensation, it's the latent heat of vaporization. And it's given by the equation where the latent heat equals the heat put into the material divided by the mass. And this ends Thermal Physics Lessons 2, Thermal Properties. Thank you.